A switch case statement is a special kind of decision maker that looks at one single value and then jumps to the block of code that matches that value. Switch expression open brace case constant 1: statements for constant 1 break case constant 2: statements for constant 2 break ellipsis default: statements when no case matches close brace. Think of a railway yard. The expression is the train and each case label is a track switch that directs the train onto a particular line. Only one track can be taken, and brake tells the train to stop after reaching its destination, instead of continuing onto the next track. The whole construct is a single compound statement that must be placed where a normal statement is allowed inside a function body, inside a loop, etc. The switch keyword starts the block. The expression is evaluated once, and the matching case label determines where execution continues. Each case label must be a constant expression that the compiler can evaluate at compile time. In C, this means an integer literal, an enumeration constant, or a defined macro, anything that does not depend on runtime data. The values must be unique. Having two cases with the same constant would make the program ambiguous, and the compiler will issue an error. The default clause is optional and works like an else. It runs when none of the case constants equal the switch expression. The default can appear anywhere in the list, but it is usually placed at the end for readability. Mathematically, the set of case constants C sub 1, C sub 2, up to C sub n must satisfy C sub I not equal C sub j for I not equal j, and the switch chooses the unique I such that expression equals C sub I if it exists. If no such I exists, control jumps to the default block if present or continues after the whole switch. When a matching case is found, execution starts at that label and continues downward until a break or a return or throw etc. is encountered. If there is no break at the end of a case, the program falls through to the next case label and executes its statements as well. This is similar to walking down a staircase without stopping on a step. You keep going until you deliberately step off. Switch day open brace case 1: print Monday newline case 2: print Tuesday newline break case 3: print Wednesday newline break close brace. If day is 1, both Monday and Tuesday are printed because there is no break after case 1. Adding break after each case stops the fall through making each case act like an independent branch. The break keyword therefore acts as a guardrail that tells the switch to exit immediately after the selected case has finished its work. If else ladder tests a series of conditions one by one until one is true. For n distinct values, the worst case time is O of n because the program may have to evaluate every condition. A switch can be implemented with a jump table. The compiler creates an array where the index is the case constant after adjusting for the smallest value. The expression is used as an index into this table, giving O of 1 time a single indirect jump. In practice, for a small number of cases, the speed difference is negligible. But for large menus, hundreds of options, a switch often compiles into a much faster lookup than a chain of if x equals v1 else if x equals v2. The code size can also be smaller because the compiler does not need to duplicate the comparison logic for each case. A rough mathematical view. An if-else ladder performs up to n comparisons each O of 1, giving total work approximately n times C. A switch with a dense range uses a table lookup costing approximately C prime, constant, regardless of n, where C prime is the cost of one array access and indirect jump. Only a limited set of data types can be used in a switch. In classic C they are int and any integer type that can be promoted to int, such as char, short, or enum. Unsigned variants, provided the values fit in the underlying range. Many modern languages extend this. Java allows byte, short, int, char, and string since Java 7. C# adds bool and string. C++ adds a num class, and with constexpr, any integral constant expression. The case constants must be compile time constants. The compiler must know their exact numeric value while compiling. This excludes variables, function calls, or any expression that depends on runtime data. Moreover, the constants must lie within the range representable by the switch expression's type. Trying to use a value outside that range produces a compilation error. Because of these restrictions, you cannot directly switch on floating point numbers, structures, or objects that do not have a well-defined integral representation. The GOTO statement provides an unconditional jump to a labeled statement within the same function. Label name colon then code, then later go to label name semicolon, which jumps to the label. The label must be an identifier that appears before a statement. It can label a simple statement, a block, or even another GOTO. The jump can only go forward or backward inside the same function scope. You cannot jump into or out of another function, nor across the boundaries of variable lifetime that require construction or destruction. In C++, this forbids jumping past a variable with a non-trivial destructor. Typical permissible targets are the start of a loop to simulate continue, the end of a loop to simulate break, and an error handling block that cleans up resources before exiting. In C, the syntax is GOTO identifier semicolon, and the identifier must be defined somewhere in the same function as identifier colon. Using GOTO changes the normal top to bottom flow of a program into a jumps and loops pattern that is hard to follow, often called spaghetti code, because the control paths intertwine like tangled noodles. Readability suffers because a reader must constantly look for the matching label to understand where execution may go next. It also breaks the principles of structured programming, which advocate using constructs like loops for a while, conditionals if else, and functions to create clear entry and exit points. While GOTO can be useful for a single cleanup point in error handling, especially in C where there is no exception mechanism, overusing it makes debugging, maintenance, and reasoning about program correctness much harder. Modern languages either omit GOTO entirely, such as Java or Python, or strongly discourage it. In short, GOTO gives you power to jump anywhere, but with that power comes loss of predictability and an increased chance of bugs such as resource leaks, uninitialized variables, and unreachable code. A common exam task is to rewrite a nested if-else structure as a switch. For example, if grade equals A, then award equals 4 else. If grade equals B, then award equals 3 else. If grade equals C, then award equals 2 else award equals 0. It can be turned into switch on grade, case A, award equals 4 break, case B, award equals 3 break, case C, award equals 2 break, default, award equals 0 break. Students are expected to show the equivalence of the two approaches and explain why break is needed after each case. Another typical question shows a piece of code that misuses GOTO. Int I equals 0, start label if I equals 5 GOTO end, print I followed by new line. Increment I GOTO start, end label, print done followed by new line. The task asks to rewrite it without GOTO using a while loop, demonstrating that the same logic is clearer. Int I equals 0, while I is less than 5 open brace, print I followed by new line. Increment I close brace, print done followed by new line. The examiner looks for identification of the uncontrolled jumps, the creation of unnecessary entry points, and the replacement with structured constructs that improve readability and safety.